welcome to my YouTube channel. Today I'm gonna show you how to do EMG timing analysis. Goal of this YouTube video is to find muscle on and muscle off, as well as muscle activity duration. So the plot you're seeing is muscle on in this line and muscle off this line, and the duration is between muscle on and muscle off. So blue plot is filtered EMG we did last time, and the red line is envelope of the EMG. So the plot above is showing the duration of each muscle in each trial. So for the first trial, seems like right semitendinosus has the most duration among other muscles, and you kind of see like same pattern of the muscle duration. Right bicep femoris is the longest duration, and the left semitendinosus is the second longest, and right semitendinosus and left bicep femoris, but except for the first trial. And also you've seen that the duration is decreasing from first trial to fifth trial. So maybe there's a fatigue or something, but in this video I'm just gonna show you muscle on, muscle off, and duration. And finally I'm gonna show you how to make a plot. You're seeing that muscle off, duration, and the x-axis is aligned same among all trials. You can easily compare first trial, second trial. You can compare one muscle with another muscle. So that's the goal of this video. Procedure. So first of all, we have to do pre-processing data. So pre-processing part is shown in my previous video. So check out my previous video. Then we're gonna do TKEO, which is Teager-Kaiser energy operator. This is a little bit complicated, but I'm gonna show you how to do this in MATLAB, and find the threshold based on TKEO, and find the muscle on and off. Then finally find the muscle duration, which is just between muscle on and muscle off. So I'm gonna show you all those procedures in MATLAB. So let's go to MATLAB. Okay, MATLAB. So this is the code I showed you in the previous video. So first of all, I'm gonna import the data. Okay, so this is the raw data, and you already saw the plot for raw data, so I'm just gonna skip it. I mean, if you want, you just go back to my previous video and you see the plot, and I explain everything about plot and pre-processing. So just check out my video. So for now, I'm just gonna skip everything about plot part. So detrain the data, power spectrum, it doesn't necessary. So filter the data. So as I said, I'm gonna do bandpass filter between 10 and 400 cutoff frequency. Then I'm gonna rectify that. I'm gonna do moving average to make an envelope. So moving average is 100. So this raw data is 2000 sample frequencies. So 100 means 0.05. So I'm gonna do moving average of 0.05 seconds. Then I just finished the pre-processing, so I'm gonna do TKEO, which is Teager-Kaiser energy operation. So the code is kind of simple. I mean, the name sounds like fancy word, but the algorithm is kind of simple. So like you just need to square of current data point and subtract the multiplication of one before the current data point and one after. So pretty much that's it. So this one line operates TKEO basically. So one thing you have to be careful is you have to exclude the first one and last one, because TKEO includes the current data point, like one before and one after. So obviously the first data point doesn't have the data point one before, right? And the same thing for the last data point. So I'm just gonna exclude that, and yes, pretty much it. And I'm gonna use filtered data. So I'm gonna run this, and this is a plot for TKEO. Pretty much the same procedure I did in the previous video. So okay, so this is the plot after TKEO. So obviously negative value is almost gone because I squared the value. So all negative point goes to positive value, but there are some negative. But as you can see, the plot is smoothed in this area and this area. I mean, like before muscle activation and after muscle activation, it's really smooth. It's almost zero. But for the activation part, it's pronounced. So later on, what I'm gonna do is find the activation. I mean, find the point which the difference between resting muscle and activated muscle. So there should be a certain threshold where muscle activation happens. Then I can find the threshold based on the difference between resting muscle activation value and activated muscle value. So TKO helps to find the threshold basically because it's more pronounced. So like I said, resting value is very close to zero and activated muscle value is more far away from zero. Then go back to the code and I'm gonna do low pass filter. So I did band pass filter before TKEO actually, but this is what research has done. So I'm just gonna follow the procedure. So low pass filter cutoff frequency is 50. So I'm gonna run this. And let's take a look at the plot. Okay, it's almost the same, but yes, so the filtering cut off some frequencies obviously. If you remember, the y-axis is from -1 to 1, but now it's -0.5 to 0.5, so obviously we lost some in the high frequencies. Then rectify the data, which means just switch sign from negative to positive, so data points should be all positive after this code. Then I'm gonna find the threshold, which is the next part. Okay, so next step is find the threshold. So I already did TKEO, low pass filtering, and rectifying. Yes, TKEO, low pass filtering, and rectifying. So what I'm gonna do is find the baseline, which should be from 1 to 1000 data point, which is before 0.5 second. Because if you remember, we have 2000 sample frequencies, which 1000 is 0.5. I excluded the first data point because if you remember TKEO, I just excluded the first data point because TKEO takes the point one before and one after, so pretty much the first one and the last one is not influenced by TKEO, or like it's not processed by TKEO, so I just exclude it. Then after I define the baseline, I take mean of it and addition. 20 is kind of coefficient. It kind of depends on what you want to analyze. So some research says if you didn't do TKEO, it should be 3. After TKEO, you can put 15 or something like that, but it didn't work in this time, so I put 20. I mean, I play around a little bit, and I think 20 works the best. And standard deviation of baseline, and that's the threshold. And I'm gonna find the value right above the threshold, which is T. And find function, I can put input the argument 1, which means I just need 1 point, which is just find the index where the value is more than threshold. You just need to take 1 data point. And the first means the find the function, find the index from the first data point to the last data point. That's the first argument means. And the last is backward from the last data point to the first data point. Then if I run this and I have the plot code right here, so I'm just gonna run this and you will see the muscle on off with filter data and envelope. So you kind of see the muscle on detection is a little bit off. It should be around right here, but now it's after 5000 milliseconds, and this one is a little bit off, but like muscle off for this plot is fine, I guess, and this one, yeah, should be fine, but some detection is, I would say, completely off. For example, right here. But like I play around and 20 works the best still. So this is based on research paper. And the second option, I mean, you can define the threshold in so many ways, but this is just one way. So based on research paper without TKEO, so I just use filter data and find the baseline. I mean the same thing, just baseline just defined like from data point 2 to 1000 and find the mean plus coefficient. I put 10 right here and the standard deviation. I also play around with coefficient and I think 10 works best at this time. I think this time it's a little bit better because if you remember the last threshold detection method with TKEO, the muscle on was like right here, but like now it's better, but it's still kind of off, and muscle off detection is off as well. This one kind of looks better, but like maybe it's a little bit around here, but I think still better than the last time. This one is completely off. It doesn't start right here. It should be around right here, and this one as well. Yeah, this one looks very fine. This is completely off. So this one is, I think, better than the method with TKEO, but not the best, I think. So this is not really based on research paper. I just adjusted for this EMG, and what I did is just I used the TKEO and find the maximum point, and the threshold is 2% of maximum value of TKEO. I'm gonna run this and let's see. Okay, I think a little bit off right here, but I think this one is okay. Yes, maybe this one is a little bit off, maybe like around here, but yeah, this one is maybe a little bit around here. This one is a little bit off as well. Yeah, so some plots maybe kind of failed to detect, but like it's not completely off, it's kind of close to where it's supposed to be. So I think this method works the best so far for this EMG data, so I'm just gonna keep this. So I actually walk around and play around. I mean, I tried so many things like TKEO with maybe 5% or maximum, or like maybe like somewhere between maximum and the baseline, blah blah blah, but like so far I think this one works best for this EMG data. So maybe you will find much better than this, but for this video I'm just gonna keep this threshold, and based on this threshold I'm gonna find the muscle on, off, and the duration. So find the duration, it's easy, it's just subtract off minus on. So I saved the muscle on and the muscle off right here by using find function, and calculation for matrix in MATLAB is really easy, especially addition and the subtraction. So you just put off and on, and you get subtraction in each corresponding data point of off and on variables. Then I run this and you get this bar plot. It's not adjusted to where the muscle activation started or muscle activation ended. It's just the duration. But like as you can see in the first trial, the right semitendinosus activated longest, and I think left semitendinosus is the second longest, and the right bicep femoris and left bicep femoris, and you can see second trial, third trial, fourth trial, fifth trial. So function use just the bar plot, and you just need to put variable right here, duration. So duration is 5 times 4 double matrix. So 5 is number of trials and 4 is a number of muscles. So okay, I'm gonna show you the bar again. So if you put the low, which is 5 or 5 trials, the bar function automatically creates bar plot in 5 right here, 1, 2, 3, 4, 5. And within the first bar plot, like a group of bar plot, you create 4 bar plot, which should be in column. If you switch the dimension, let's say 4 times 5, you create 4 groups of bar right here, and within the one group you create 5 plots. So So order should be 5 times 4 in this time because I just want to make a group in trial wise. But like if you wanna make a group for like a muscle wise, you have to flip the dimension. Then it's easy, just put the legend and X label, Y label, and title. Save as is the function to save the picture or plot right here. You just create a handle for the figure and put it inside of save as function and put the name. And you can define the data format. It can be PNG, it can be JPEG, so you can choose whatever you want. And after that, I'm gonna make a plot for muscle on and off with duration. So I'm gonna run this and you will see what I mean. So on this plot, unlike the last bar plot, you can see when muscle started activation and when muscle ended activation. And x-axis is a line among all trials, so you can actually compare one trial with another trial. And of course you can compare one muscle with another muscle. So how did I make it? Obviously the plot itself is subplot, so I just used a subplot and I created 5 subplots in total, and within the subplot I created 4 plots basically. So first input argument is x-axis, so x starts from muscle on right here and end with muscle on plus duration. So plot create a line from muscle on to whatever it was. So on plus duration, it should be muscle off. And the y-axis is just from 1 to 4 because 4 muscles in total. I created a little bit walk around, so y here is from 4 to 1, not from 1 to 4, because I want to plot from above to the end. If you just use counter variable k here, the plot is just blue goes to here, which is 1 y-axis, and red goes to the second y-axis, and so on. And legend recognize the first loop is on the top of the legend right here. So it doesn't really matter because color doesn't change, but for just better looking, blue is always top, red is always second, yellow is always third. That's why I just use y. I just define the y from 4 to 1. So the line actually goes from top to bottom. Then it's aligned with legend. Then I just created the y label with starcat function. So starcat function is just combine one string with another string. So I just put trial with counter variable I, which is right here. So because since there is 5 trials in total, this I goes from 1 to 5, and the trial 1 goes first, and the 2 the second, 3 the third, and so on. And I just rotated the y label. So trial 1 is now 0 degree, default is 90 degrees, so trial is in this direction in default, but I just rotate it, fix it to 0 degree, which is horizontal from left to right basically. And I change the position because the default is a little bit like right here, it's almost merging with this line. So I wanted to move the y label a little bit to left or like far away from this line. So that's why I put -2000, which is horizontal value, and the 2.5 is the vertical value. Then y lim is y-axis, should start from 0 to 5, and x lim is same thing but in x-axis. And I put the legend and x label, it's time in millisecond. Then I put the title. So common title for subplot, you can use SG title instead of title, but like I think as far as I know, if you use save as function, the title doesn't appear in the figure you save. So that's why I use the title and put the first subplot in here. So I saved all subplot data into variable called s, and the first subplot is always the top. So here, this is the first subplot, and I put the title of basically the first subplot, not for the common, but like kind of same thing because title is always the top of all subplots. So this is basically the title for all subplots. But like I just did walk around. I just used title function and defined where I should put the title right here. Then save as function works really good. It includes the title on the picture, so I just saved it. Then pretty much that's it. So that's EMG timing analysis, muscle on, muscle off, and the duration. So for the next video, I'm gonna show you how to compare or how to find amplitude comparisons between muscle or trial, or frequency comparison between muscle or trial. And of course, I'm gonna put this MATLAB code on my blog so you can download it, play around. So see you next time.